Good afternoon, everyone. My name is Pengcheng Dai. I come from Beihang University in China. My title today is SparseTrain, Exploring Dataflow Sparsity for Efficient Convolutional Neural Networks Training. I will talk about my work mainly in three aspects: algorithm, data flow, and architecture. After that, I will show you the experiments and results, and finally, I will make a conclusion. We all know that deep learning has become a powerful tool in many areas. In particular, convolutional neural networks, or CNN, performs very well in most of the computer vision problems. However, in the past few years, although the precision of CNN models become higher and higher, the size of the models is growing rapidly as well. Thus, specific designs from algorithm to hardware are needed to achieve a higher speed and efficiency. There are many works to improve performance of CNN models, including model compression, quantization, specific hardware designs, and so on. Among all these works, we found exploit sparsity is a useful way to improve both speed and efficiency. Many previous works use sparsity only in CNN inference instead of training. However, in modern CNN applications, training requires much more time and energy than inference. That inspired us to make use of sparsity during CNN training. There are different types of sparsity in CNN. Figure A is a traditional CNN algorithm. It does not consider the data sparsity. They just perform convolutions between weights and activations. Figure B is a model compression method that providing weight sparsity. In this method, model weights are primed after training. In this way, they get very sparse weights, and the weight sparsity can be used to accelerate CNN inference. Some works make one step further on utilizing sparsity. Like Figure C, they found that not only weights, but also the activations can be sparse during inference. The activation sparsity is usually obtained from ReLU layers, because the ReLU layer will set negative activation values to 0. These works achieve higher performance, but also require more complex data flow or hardware designs. However, all these works are aimed to accelerate CNN inference instead of training. To bring the benefits of sparsity into training, we try to find more sparsity that can be used in training. Some works on distributed training make use of compressed weight gradients to reduce communication overheads, but we still need to find a way to actually reduce computational complexity. Finally, we bring sparsity into our training gradients and utilize it for training acceleration, as we can see in this figure. In our algorithms, sparse gradients appears in every step of back-propagation, which dramatically reduces the computational complexity. In fact, gradient sparsity naturally exists in the training process. This natural sparsity also comes from ReLU layer. But typically, natural sparsity is not high enough. We still need to introduce artificial sparsity on our gradients. Besides, to truly benefit from gradient sparsity, we also need to control the overhead of sparsity utilizing and make it compatible with data reuse. But before this, let's talk about how to get higher gradient sparsity. The basic idea is simple. We can perform gradient pruning before each conv layer during backpropagation, or we can say BP. Problems exist in the convergence. Each time we do pruning, we actually add some noise to the gradients. With gradients backpropagate through layers, the noise will be amplified and the training will not convergence. So how can we do, or what can we do? To overcome this problem, we use two tricks. The first one is only the gradients with small absolute value will be pruned. Gradients larger than threshold is maintained. Secondly, when a small gradient is pruned, it is not set to 0 directly, but it is set to threshold all 0 stochastically with a probability p. We found that if the mathematical expectation after pruning is equal to the original value, the training will convergence. That's what we do for pruning. The threshold that determines whether a value should be pruned is calculated from target sparsity. Though sparse data provides large potential of acceleration, modern CPU and GPUs can hardly benefit from it. We need specific data flow and architecture to take use of it. Most of the operations in CNN are two-dimensional convolutions. A 2D convolution can be seen as the sum of many 1D convolutions. Following this way, all three steps of training, including forward, calculate gradient to activations, and gradient to width, we can call the later to GTA or GTW. All the three steps can be divided into a bunch of 1D sparse convolutions. Our architecture will work with the 1D sparse convolutions, and it is much easier for hardware to efficiently compute 1D convolutions than 2D convolutions. There are some tricky points in the data flow. For example, if we want to prune the gradients as long as it is generated, we must predict the threshold of pruning. What's more, specific data formats are needed for the efficient sparse operations. These details can be found in our paper. To support the sparse training data flow, we design architecture. In this architecture, all processing elements, or we can say PEs, form an array. Each PE performs a 1D sparse convolution. PEs in each column are in the same group. Each PE group will add the results together to form the output. Different PE can share the same inputs. In this way, we can reuse different types of data. Corresponding to the three steps of training, PE can work in three modes. Each mode has a different type of sparsity, but the main process of them is the same. Thus, we can share the same data path. Except for PE, there is another type of unit called post-processing unit, or we can say PPU. This unit will perform some simple operations such as ReLU or data format transformation and so on. All the PE and PPU are managed by the pre-compute instructions and perform the operation for each layer. The proposed method can provide the high sparsity with negligible accuracy loss. This table shows the training accuracy for different target sparsity. As we can see, the training accuracy hardly decreased, even in 17% to 90% sparsity. The training convergence is also maintained. The training convergence basically is the same with the original algorithm, unless you use very aggressive policy, like 99.5% pruning rate, like in the figure C, the top, the line on the top, it's have less convergence than others, but in most of the time the convergence is basically maintained. For performance, the gradient pruning algorithm can decrease running time, product operations, memory access by 63%, 88%, and 59% respectively. And overall, in our simulation, our SparseTrain architecture can achieve 2.7 times speed ups and 2.1 times more energy efficiency on average. The scalability of SparseTrain architecture is also great. As we can see in the figure at the bottom. As the P number grows, the training latency has an inverse relation with the P numbers. That means this architecture is easily scalable and has a linear speed up ratio. In conclusion, in this work, we proposed a gradient pruning algorithm that fully exploits sparsity in CNN training. To make full use of data sparsity, a one-dimensional convolution-based training data flow is designed. We also design an architecture to support this data flow with high performance. With all the sparsity utilized, SparseTrain, our architecture can achieve 10% gradient sparsity at most, with negligible accuracy loss. It also achieves 2.7 times speed up and 2.2 times more energy efficiency with great scalability. And that's all my presentation today. Thanks for listening. Thank you. If you have any questions, please feel free to contact me. Thanks again.